doing the hypothesis testing is really just building on what we've done before. Finding the probability of something, which is what we did the whole last chapter. The difference is at the end we have to decide, does this support or our hypothesis or not. We can also use it with confidence intervals. Remember, we've built confidence intervals before. We can find a confidence interval and see if our null hypothesis value is in that interval or not. So if our null is included in the interval, we would fail to reject. If the null was outside, then we would reject. So we can look at it that way as well. Remember when we did confidence intervals, we had formulas. Does everybody have their formula sheet handy? So back when we did the confidence interval stuff, it's been a little bit. That is, okay, under chapter 9, we have all the bullets for confidence intervals. Right now we are focusing on p-hat, so that first bullet is the formula that we used. We also, a lot of times, just did confidence intervals on our calculator. So we'll talk about both options with that today. So let's look at an example. A 2009 study found that 34% of teenagers text while driving. A more recent survey found that 353 of 1,200 randomly selected teens had texted while driving. Does this suggest the number has changed since 2009? Use a 95% confidence interval to answer the question. So I'm telling you, don't do the p-value approach here, build a confidence interval and see. If we're going to do this, we need to have a null and alternative hypothesis. We're also going to have to check our criteria. So that's where we need to start. The null hypothesis. We're talking about anytime we see percents, we're looking at the proportion. Null hypothesis is always equal to, so proportion equals 0.34. What would be my alternative? Yeah, I just want to know, has it changed? So that would be not equal. Verify your criteria. I told you we can pretty much assume the 5% rule is going to be followed here, so we really just need to check n times p times 1 minus p. So my n was how many? 1,200 times p, which is 0.34, times 1 minus 0.34. I need this to be larger than 10. That's good. We're also going to need to find our p-hat. We know p-hat is x over n. So what is it in this scenario? So we get 0.2942. All right, if you look at your formula sheet, our confidence interval was p-hat, which is 0.2942, plus and minus, we need a z alpha over 2. Right, so if I want to find this, we want a 95% confidence interval, right? So if you look at your normal table, remember at the bottom for the confidence interval, it had a lot of the common z alpha over 2s, and it told us for 95% z alpha over 2 is 1.96. Right, if you're following along on your formula sheet, it says times the square root of p-hat times 1 minus p-hat divided by n. we're just getting an interval. So you could type this in. I always do the -1 first. If you hit second enter, you can bring it back up to be the plus. Okay, just set it up here. Thank you. Did everybody get that? Do you remember how to do these on our calculator? So if we go into tests, we know we want an interval. We know when we're talking about p's, it's always a z. You'll know if you pick the wrong one. If I see like number 7, z interval, when I look at that, do I have a sigma? No, it's asking me questions I don't know. So let's see if there's a better option. So when I go through here, we know we're dealing with z's. We know we want an interval. So A, 1 proportion z interval. And then it's asking me questions we can answer. My x was 353, n 1,200, confidence level 0.95. And if we calculate, let me see that these two match. So unless I specifically said by hand, you could do it either way, calculator or by hand. So now the question is, we have to make some kind of conclusion. I want to know if this suggests the number has changed. So you're looking. Our null hypothesis was that the proportion is 0.34. Is 0.34 in this interval? No. So I'm going to write out so we are 95% confident the true value is between these two numbers. Since 0.34 is not, that means it would be very unusual to have 0.34, so we will reject the null hypothesis. That means there is evidence the proportion has changed. Questions there? The last one that I want to go through is a little bit different. I'm going to go ahead and tell you right now, there's one on the homework, but I will not put this one on a test or a quiz. Okay, it's a little more challenging. We should go ahead and talk about it, but it'll only be assessed on the homework. So we know that we have seen binomial distributions before. That was way back before we did the normal distribution. Binomial was when we had a fixed number of trials and there were only 2 possible outcomes. Like if I'm going to flip a coin 5 times. Okay, you either get a heads or tails. There's only 2 outcomes. We know we're only doing it 5 times. Remember in chapter 6, I think it was, I gave you a whole other formula sheet that was like a binomial table that had all of those probabilities for us that we relied on. And there was also a formula to calculate it by hand. Sometimes we have data that we want to be able to apply this to, but the criteria isn't met. Okay, we know that in order to be able to do anything we're doing, we have to satisfy the criteria. N times P times 1 minus P has to be bigger than 10. If it's not, then we don't just want to give up and say we can't solve this problem. We have to have a different approach. And in that case, we use the binomial. So when the criteria fails to be met, we have to stick with the binomial. Okay. So when I look at this one, in 2006, 10.5% of all live births in the United States were to mothers under 20 years of age. A sociologist claims that births to mothers under 20 years of age is decreasing. She conducts a random sample of 34 births and finds that 3 of them were to mothers under the age of 20. Test it at the alpha equals 0.01 level. All right, so my null hypothesis would be that P is equal to what? 0.105, the original. The alternative, she believes that it is decreasing. So the alternative would be that P is less than 0.105. So we know we have to check our criteria. My N is what? $34. P, 0.105. 1 minus 0.105. Okay, this is smaller than 10. So that means this is not normal. We cannot use the normal table and that approach to get there. So instead, we have to use binomial. Okay, we're still just trying to find the probability of this happening. So we need to look at, remember, do you guys have your binomial tables handy? What was the downside to this binomial table? Did it have every possibility on it? No, it gave us n values. 2, 4, it went all the way up to 12, and then it gave you 15 and 20, and then it stopped. Because we saw, you know, when n is 20, we saw that took half page to put that table on there. So can we rely on this all the time? No, we had to use the formula for the rest of the time. When I'm looking at this, if my n is 34, this table is not enough. It doesn't go up to 34. So we would actually have to do this by hand, which is a little more time consuming. We also, didn't I show you how to do binomials on the calculator?
I think we did that.
It's hard to remember way back when. So let's talk about how we might do that. We want to find the probability, since we're looking at less than, let's find the probability that x was less than or equal to the 3. Because that was she found 3 in her study. So that means we have to find the probability of 0, 1, 2, and 3. And we're going to have to add all 4 of those numbers together. If we are doing it by hand, if you look on your formula sheet, back under chapter 6, the third bullet down, gave us the formula. Remember, we had to do the n choose x, so this would be 34 choose 0 in case of the first one. And we can work through it that way. I want to show you just how to do it on our calculator here. Be a little more useful. So on the calculator, you have to go into second, and then over here by your clear button there's a VARS. So we're going to hit second and that VARS button, and this gives us all kinds of distributions. We are not looking for normal, we are looking for binomial. So we are going to have to go down until we find binomial. Okay, so A has binomial PDF, B is binomial CDF. PDF is what you would do to just find each individual probability. So if we go to that, we have to do each of these 4 things and then add them together. CDF will actually add them for us. So we're going to go into that one, CDF. All right, trials. That's our N. How many times do we do this? 34. P, what probability are we looking at? 0.105. X, we're trying to go up to x equals 3. And if we just hit enter, it will actually find the probability of everything less than 3. So hit enter one more time. Oh no, what did I do? Yours were? What did I type in wrong? Anybody else get an error? Just me? Ah, I missed a decimal. Sorry, I'm struggling with this one. All right, so you got 0.5149. Remember, when we're doing this p-value approach, when do you reject? If p is less than alpha. So 0.5149 is bigger than alpha, so that means we fail to reject. There is not enough evidence that the proportion has changed. Okay, so yesterday you were able to do everything except the last 2 in section 10.2, so this should wrap that up. Are there any questions over those 2 examples? I want to do just a little bit out of 10.3 if we could, so that tomorrow we'll also have time to work on homework. So I'm going to teach 10.3 for a little bit and then give you time to finish the 10.2 homework. So this is still more of the same thing. It's still hypothesis testing, so we still have all the same approaches, p-value, classical approach. The difference is we are testing for the population mean instead of the proportion. So when we're talking about a proportion, our variable is p. When we're talking about the mean, our variable is mu. So remember when we went back in chapters 7 and 8, we talked about mu's and p's. It's all the same thing here. We're just looking at the other variable now. So requirements, remember for the population mean, the requirements were a little different, our criteria. With this one, what we needed to focus on is I either had to tell you it was originally normally distributed or n had to be bigger than 30. So when we're talking about p, that's when you have to have the n times p times 1 minus p bigger than 10. When we're talking about mu, either I have to tell you it's normal or my sample has to be bigger than 30. So then, same idea after that. We do the null and alternative hypothesis. We have to look at our alpha level, which will be given in our problem. We will have to find, in this case it's called a test statistic, which is a t statistic. It's really the same thing as a z-value. It's your original or your value minus the mean of the null hypothesis divided by standard deviation. So it's really the same thing as a z, but we use t for this variable. And we have the degrees of freedom that come into play with this. Hopefully some of this is ringing a bell, degrees of freedom we have seen before. Then you have the classical versus p-value approach. Classical, you are basically measuring the standard deviations from the mean. I think we kind of decided yesterday we don't really prefer that one. So we're going to stick with the p-value approach more often. And my board just froze. So that's nice. P-value approach, still we get our t, and then we're looking at our probability, and if we reject when it's smaller than alpha. So same kind of scenario. Let's look through. We'll do it by hand, and then I'll also show you how to do it on the calculator here. So assume the resting metabolic rate of healthy males in complete silence is 5,710 kilojoules per day. Researchers measured the RMR of 45 healthy males who were listening to calm classical music and found their mean to be 5,708.07, standard deviation of 992.05. At the alpha equals 0.05 level, is there evidence to conclude that the mean RMR is different? So same initial setup, we need a null and an alternative hypothesis. But what is my variable here? Mu. I'm not talking about a proportion, I'm talking about means, so that's mu. So the null would be that mu is equal to 5,710. I'm trying to test if it's different, so different would be not equal. Criteria, if I'm talking about mu, either I have to tell you it's normal or n has to be bigger than 30. My n was 45, so 45 is bigger than 30, so my criteria is satisfied here. We can move forward. Okay, what we did before with the other, at this point we had to find our z-value, right? So we need to know the mean and standard deviation to do that. So let's get our mean. The mean for this, if you look on your formula sheet, under chapter 8, the first bullet, the mean and standard deviation for x bar, or the sample mean, is just mu, so that would be 5,710. The standard deviation, it tells you is sigma over n. So sigma is the standard deviation of our population here, which was divided by the square root of n, so the square root of 45. So we get 147.8861. Okay, here is really the only difference Instead of calling it a z, we're going to call this a t value. So our t is it's just like finding a z, it's our value, so our mean was the 5708.07 minus the original mean divided by standard deviation. Bless you. So now we have to find the probability of this. Remember yesterday we did one two-tailed example with the not equal, and I talked about how when we're doing not equal we have to do both of these and add them together. If you look on your formula sheet, we are talking about the t distribution. So we saw this on the last test. You have to go flip your page, not the normal table, the t table. It's on the back of that normal. Okay, and it has along the side degrees of freedom. Remember, degrees of freedom is always n minus 1. So 45 minus 1 means we have 44 degrees of freedom. Does this table go up to 44? No, it's not perfect. So the closest we could do would be 40 if we're trying to use this table. And then we had across the top, we had these different levels. Okay, so when we are looking at this, we have to find both tails, so we're going to multiply it by 2. This one gives us the higher one. And then do you guys remember how to find this in the table? We're trying to get the closest we can. So 0.013 is not great, but we want the closest we can get to that. So it's like saying this right here is 0.013. So we have to find the closest area that we can. So if you're looking on the 40 row, these are the different areas down here. Are any of them close to 0.013? Yeah, if we're looking within the table, the best we have on that row is 0.681. Is that even very close at all? No. The probability that corresponds to that, if you go up to the top, is 0.25. And so if we multiply that by 2, we get a 0.5, a 50% chance. But we know this is really bad because we didn't have the degrees of freedom that matched. We didn't have the probability that matched the 0.013. So the table for this is extremely limited. So for that reason, we are going to rely on the calculator for these problems because we are so limited on what we can do. So this will be where we end today. I'm going to show you how to do this on our calculator, and then we'll do more of these tomorrow. So on your calculator, you are going to go into Stat, Tests again. Okay, this time we're not looking at Z's, we're looking at T's. And so we just want to go to number 2, a T test. Okay, it gives us the option, data or stats. We want to go off stats here. Mu sub 0, so the mean of our null hypothesis was 5710. X bar, that's the mean of our sample, 5708.07. S sub x, the standard deviation of the sample, so the standard deviation given in the problem was 992.05. N, we had 45. We're testing not equal. We'll come down and calculate. All right. So when we look through this, it gives us our t statistic. What is the actual probability here? You can see how far off we were. We estimated a 0.5 using our table. It's actually 0.9896. Now, either way, we would have had the same conclusion. These are both bigger than alpha, so what does that mean? We would fail to reject. Okay, it is extremely likely to get this answer if the null hypothesis is true. There is almost a 99% chance that we get this value, so we would definitely assume that our null hypothesis is still true. All right, we will do more